Jai Hind to all. Today I am presenting my third lecture on subject signal system KEC 403. I am Dr. Amit Garg, Associate Professor in EC Department of AKGEC, and the topic is signal transforms. So basically in this particular lecture, what I will try to do, I will explain all the transforms that are necessary at your level, and and also try to give a comparison among all those three transforms. Okay, so let us start with, first of all, I would like to start with decomposition of a signal. So why we are using transforms and all those things? Generally, transforms that we are using are used for basically for moving from time domain to frequency domain. Means there are some signals. If you want to analyze those signals in time domain, then the information is not sufficient. Okay, so what we have to do basically, so that we will transform the signal from time domain to frequency domain, and you can say in frequency domain more information is available. So why we are doing all this? So for this, first of all, see decomposition of the signal. So the goal of signal decomposition is extraction and separation of signal components from composite signals, non-stationary signals. Okay, so you can see if the signal is composite, then there will be more than one frequency component present in the signal, and in case of non-stationary signal, again this is the issue. So if your signal is stationary, let us suppose, stationary signal means simple, this is your stationary signal. Okay, so if you are taking a stationary signal, then it is very easy to analyze the frequency component of this signal, because let us suppose this is 40 Hertz signal. So if you will see it in frequency domain, you will get a spike at 40 Hertz. Okay, so that is you can say quite easy. So for this type of signals, frequency analysis is not required. But if we are having a non-stationary signal, or you can say a random type of signal, in that case, frequency, it is important to know. That what frequencies are actually present in this signal, and also we would like to know that at what time those frequencies are occurring. Okay, so this is the role of signal decomposition, that by decomposing the signal, we can obtain the different frequency components present in the signal. Okay, so you can say all transforms are basically decomposition techniques. So signal decomposition technique includes, you can say, one way is Fourier series representation. You have all go through the Fourier series representation. So Fourier series representation is what? It is the representation of 9 non-sinusoidal signals over a certain interval time in terms of linear combination of orthogonal functions. So what are the orthogonal functions for Fourier series representation? That depends upon the type of series we are taking. So in case of trigonometric Fourier series, orthogonal functions are trigonometric functions like sine and cos, and in case of exponential Fourier series, orthogonal functions are exponential functions. Means we will represent our signal in terms of trigonometric functions or exponential functions, okay, with different harmonics. Okay, so you can say Fourier analysis is a tool which changes a time domain signal into a frequency domain signal and vice versa. And the use of Fourier series representation, that it is applicable for the analysis of periodic signals only. Okay, so if we are having a signal which is periodic signal, so for that we can do the frequency domain analysis using Fourier series representation. Okay, so I am not going through so much in case of Fourier series. Next is Fourier transform representation. Okay, so Fourier transform is a mathematical tool which changes a time domain signal into a frequency domain signal and vice versa, and it is used for the analysis of aperiodic signals. So this is basically the difference, you can say. In case of Fourier series representation, we are analyzing a periodic signal, but here we will analyze the signal mainly, that is aperiodic signal, and also we can also do the analysis for periodic signals. Generally, we are using the Fourier transform representation for periodic signals, for those periodic signals only for which Fourier series representation cannot be taken. Means we are only considering periodic signals for Fourier transform representation for which Fourier series representation is not possible, or you can say difficult. Okay, so now let us understand what is this transform. Transform means you can assume it like we are having a prism, and you can say one white light is entering from this point, and you are having 7 color light here. You know that is Vibgyor. Okay, V2R you will get, and here it is white light basically. So you can say the person who is standing over here is saying that this is white light, and the person who is standing over there is saying that it is 7 color light, or the light is light consists of 7 colors. So you can say definitely here is the more information. So like this we can say here is the time and here is the frequency. Okay, so you can say in frequency domain we will get the more information. Okay, or you can say time, or you can say there is no change in the signal from here to here, but visualization is different, means we are getting more information from the same signal here, but here the information is less, you can say. Okay, so you can say or you can think about that there will be no change, there will be no change in the signal, but the change in the information in the signal while we are doing the transform. Okay, next, why frequency domain representation? Because it allows us to observe several characteristics of the signal that are either not visible or not easy to see in time domain, that I have already explained. Like cyclic behavior of a signal can be seen in better manner in frequency domain as compared to time domain. So if you want to see the cyclic behavior, then in that case frequency domain representation is more appropriate as compared to time domain representation. Okay. Now we will see the types of transforms that generally we study in our curriculum: continuous time Fourier transform, discrete time Fourier transform, discrete time discrete Fourier transform, Laplace transform, jet transforms. Okay. So because all these are transforms, so all these transforms are used for the analysis of aperiodic signals or for periodic signals for which Fourier series representation is not possible. Okay. So for all these transforms we will see this. So first of all, let us start with continuous time Fourier transform. So continuous time Fourier transform specifies the spectral component of a signal, thus providing a frequency domain representation of the signal. And an aperiodic signal can be represented as a linear combination of complex exponentials which are infinitely close in frequency. So the representation takes the form of an integral rather than a sum. So in continuous time Fourier transform, if you will see your signal xt, let us suppose you are having a signal xt, so your xt is basically continuous. Okay, and when we will take its transform, let us suppose a transform of xt is, let's say, x omega. It is represented like this. So you can say here xt is continuous and here x omega is also continuous. This xt is aperiodic generally, and it is also, you can say, aperiodic. Okay. So example, in the Fourier series representation, as the period becomes infinite, the frequency components form a continuum and the Fourier series becomes an integral. So this is how we are changing the expression for Fourier series to get the expression for continuous time Fourier transform, because here you can assume an aperiodic signal with infinite period. Okay, so you can say in time, in frequency it will become 0, or you can say all the frequency components will be overlapped with each other. So those points are not discrete but in a continuous manner. So that's why we have replaced the expression. So the expression for Fourier transform is this, xt into e to the power minus j omega t dt minus infinity to infinity. And if you want to obtain the inverse Fourier transform, the expression is xt equals to 1 upon 2 pi minus infinity to infinity x j omega e to the power j omega t d omega. Okay, so it means, so the resulting spectrum of coefficients in this representation is called the Fourier transform, and this is basically, you can also call analysis equation, and this is nothing but synthesis equation. Okay. So what is x j omega? X j omega, or you can also write it x omega, is the spectrum of xt, and it is a continuous function defined for all values of omega. Like we have seen previously, I have told you, this is a continuous function and this is also a continuous function. So you can see, if you are having a signal, continuous time signal, and you are taking it CTFT, then you are having a spectrum which is continuous from minus infinity to plus infinity. Okay, and if you want to extract this signal again from the Fourier transform signal, then you have to take inverse Fourier transform. So you have to take the entire spectrum minus infinity to infinity to obtain the signal again. Okay. So this we have, I think, already discussed. Now you can see how we will represent it. Like x omega can be represented like this, Fourier transform of xt, or you can write it like xt is the xt equals to Fourier inverse of x omega, and this is the representation. Okay. So generally what happened, this x omega is a complex quantity or complex function of the variable omega. So it can be written like x omega will be xr omega plus jxi omega, and x omega will be mod of x omega into e to the power j angle x omega. So this mod of x omega is nothing but under root of real part ka square plus under root of imaginary part ka square, and this angle of x omega is nothing but tan inverse imaginary part upon real part. This is the angle or phase of x omega. Okay. Next is DTFT, discrete time Fourier transform. So in case of discrete time Fourier transform, we will use a discrete signal. Okay. For discrete signal, we will calculate discrete time Fourier transform. So if we take the discrete time Fourier transform of a signal, discrete signal, then it is generally represented by x e to the power j omega. Again here omega is continuous. Here again omega is continuous. Okay. So you are having a discrete sequence and you are taking DTFT, and the spectrum that you are getting is again continuous. Okay. So we can see this also. DTFT is simply the Fourier transform of discrete time sequence xn. It is represented by the complex exponential sequence e to the power minus j omega n, where omega is the real frequency variable. This transform is useful to map the time domain sequence into a continuous function of a frequency variable. This we have seen, and it is applicable both for infinite and finite time duration sequences, and also periodic with period 2 pi. So these are the expressions for discrete time Fourier transform. Here we will, because sequence is discrete, so we will take this summation n equals to minus infinity to infinity xn into e to the power minus j omega n. Okay. So the major difference between CTFT and DTFT, if you will see, the major difference is that in case of CTFT, you have seen if you are having a signal, so you have seen that the spectrum that you are getting is basically like minus infinity to infinity. This is for CTFT. There is no periodicity and it is aperiodic. But if you will draw the spectrum for DTFT, in that case, there will be a periodicity in the spectrum like this. So you can see here is the periodicity, and this is period is from 0 to 2 pi or minus pi to pi. So you can say while taking DTFT, the whole information or x e to the power j omega or the DTFT information is contained in each cycle equally. Means you can say if you will take the DTFT, then the obtained information is periodic, means the information that is here is also here, is also here, and also here. Okay. So we don't require so many periods. We will take only one period in that case because the information is same. And if you want to extract the signal again from this period 0 to 2 pi, then what we have to do, basically we have to take inverse Fourier transform. But in this case, like here, if you want to extract the signal xt, then we have to take the entire spectrum. But here we will take only, but if you want to extract the signal from here xn, then you have to take only this period of 0 to 2 pi. So that's why the expression is xn equals to 1 upon 2 pi minus pi to pi. You can take 0 to 2 pi or also minus pi to pi. X e to the power j omega into e to the power j omega and d omega. So this is the equation for IDTFT. Okay. So this is just I'm showing that how DTFT is periodic. So if you are seeing this, DTFT is periodic in omega with a period 2 pi. So you can see this. We will take this x e to the power j omega plus 2 pi will be equal to x e to the power j omega. Now we know the definition of x e to the power j omega. This is this definition. Now what I am doing, I am multiplying with e to the power j 2 pi k on both sides. Okay. So it will become, you can say like e to the power minus j omega plus 2 pi k times n, and we will separate it out, and we know this, the value of this. Actually what happened, the value of this is you can say simply 1. Why? Because k and n both are integers. Okay, so e to the power minus j 2 pi will become cos 2 pi minus j sin 2 pi, or if you are assuming that k and n both are n, so it is e to the power minus j 2 pi, it will become cos 2 pi minus j sin 2 pi, which will be equal to 1. If we are assuming any values of k and n integer values, then always it will become 1. So we can obsolete this term, so we will get this expression. So we can see this x e to the power j omega plus 2 pi k equals to x e to the power j omega. It means it is periodic with period 2 pi, and that that interval, frequency interval will be 0 to 2 pi or minus pi to pi. Okay. Now we come to the discrete Fourier transform. So in case of discrete Fourier transform, you have seen that in case of DTFT, we have taken only one interval of 0 to 2 pi. Okay, but again if we will see the values, it is a function of omega only. It is a function of omega only, and omega is a continuous variable. So what happened in case of DTFT, the spectrum that we have obtained is still continuous. So if it is continuous, so between 0 to 2 pi there are infinite number of possible values of omega over which we will obtain the Fourier transform. But if you want to process the signal through a digital computer, then in that case what happened? Then in that case it is a must that your signal as well as its transform is basically discrete. Only then can final values will only then can be you can say you can process it using a digital computer. Means your input should be discrete and your output should be discrete. And also another thing is that the values that we are taking are also finite. Okay, for infinite values you cannot process it using digital computer. Okay, so what we will do in case of DFT, what we are doing, we are basically sampling this one period of DTFT, and let us suppose and these are discrete values like 0, 0, 1, 2, 3 like this. These are discrete values. Okay, so let us suppose this overall separation is 2 pi and we are dividing it into n equal parts. Okay, so n equal parts means the separation between two sample is 2 pi by n, and we are choosing an index, let's say n, let's say k, and we are varying the value of k from 0 to n minus 1. So what happened? So if you write 2 pi k by n, then using this index we can reach at any value where the value of k is varying from 0 to n minus 1. So what we have to do for the expression of DTFT, what we are doing, you can see the expression of DTFT is xn into e to the power minus j omega n. Now in place of omega, to make it discrete, we are putting 2 pi k by n. So now you can see the expression will become e to the power minus j 2 pi n k by n. So in place of omega, you have simply put 2 pi k by n. Okay, and k value is 0 to n minus 1. And also here we can see that the sequence is also from n equals to 0 to n minus 1. Actually, what happened? There will be there is a condition that here we are dividing the spectrum into n parts, and here is the length of the sequence. So let us suppose length of the sequence is L, and the number of points of DFT we are taking as n. Then always it should be if we want to reconstruct the signal completely, then always you can use this condition n greater than equal to L. Means n can be greater than L or equal to L. And for analytical easiness, we are generally choosing it n equals to L. So that's why we are putting here n. So means the number of points you are taking for taking DFT is similar to the length of the sequence. Okay. So this is the expression of DFT, and corresponding IDFT, if you will see, this is the expression 1 upon n times summation k equals to 0 to n minus 1 xk e to the power j 2 pi n k by n. So here you can see there that minus sign is not here, and again because we know xk this time, so we have to calculate this for the values of n, small n. Okay. So by this manner you can calculate the IDFT. Okay. So CTFT, DTFT, DFT we have seen. So you can see this slide. By this you can understand what is the difference. So you can see in CTFT the signal is a continuous and aperiodic, but here the spectrum is again continuous and aperiodic, and here infinite length aperiodic discrete sequence. In case of DTFT, we will generally use this. It may also be possible that the length of this is finite for finite length signals also DTFT is possible. Okay, but you can see in this case you are getting, you can see this 0 to 2 pi, it is repeating itself. Okay, so spectrum is continuous but periodic with period 2 pi. And third, DFT, in case of DFT we have seen that we have taken the discrete sequence, and because we have to process it computer, so we cannot take the values as infinite values. So you have to always take finite values. So this is also an important thing, that these sequences are periodic. Okay, so the sequence is discrete and periodic, and also the spectrum that you are getting is discrete and periodic. Okay, now come to the Laplace transform. So we have seen CTFT. So Laplace transform is nothing but extension of CTFT. Extension of CTFT. Okay. So this is basically we are using for those signals for which we cannot obtain CTFT. Okay. Laplace transform is generally used for those signals for which we cannot analyze the signals for which CTFT cannot be taken. Okay. So the problem associated with CTFT is that many of the input signals do not have Fourier transforms. Like you can see the example e to the power at ut for a greater than 0, e to the power minus at for range t minus infinity to infinity, or tut, and other signals. And all these signals are not absolutely integrable signals. So you can say for absolutely integrable signal, these signals that are not absolutely integrable, we will use Laplace transform. Okay. So because the Fourier transform does not exist for signals that are not absolutely integrable. Now this difficulty could be resolved by generalizing the Fourier transform so that signal xt is expressed as a sum of complex exponential e to the power st. So rather than taking e to the power j omega t, we are using it e to the power st, where s equals to sigma plus j omega. So in case of CTFT, our analysis sigma part is 0 in case of CTFT. So what happened? If sigma part is 0, so our analysis is accepted only on the imaginary axis. Okay, but if we will take this analysis for any value of sigma here, here, or here, then it is possible that your signal is absolutely integrable at these values of sigma plus j omega. Okay. So what we will do? So this is equivalent to multiplying the signal by an exponential convergent function, for example, e to the power minus sigma t. E to the power at ut satisfied Dirichlet condition for sigma greater than a. Okay. So this is basically, you can say, extension of CTFT. So we are converting a signal to a domain which is a complex frequency domain, and this Laplace transform possesses a distinct set of properties for analyzing signals and LTI systems, and many of Laplace transform properties are similar to those of CTFT. If you will simply put s equals to j omega in the expression of Laplace transform, then you will get the corresponding expression for Fourier transform. Okay, and Laplace transform can be applied for the analysis of unstable or stable systems both, as compared to CTFT, where analysis is only restricted to stable systems. Okay, so Laplace transform comes into two varieties, bilateral or unilateral. Bilateral transform is generally used when we are interested in finding out the stability, causality, and frequency response of the system, and unilateral Laplace transform is basically a tool by which we can solve the differential equation with initial conditions. Okay, so the expression for the Laplace transform is this: minus infinity to infinity xt into e to the power minus st dt, and in case of unilateral, the limit will be from 0 to infinity, and Laplace inverse Laplace transform expression is given this. Generally, the result is very complicated, so there is no requirement to use this particular expression for finding out the inverse Laplace transform. We are having another method by which we can calculate, like partial fraction is one method by which we can obtain the inverse Laplace transform. Now region of convergence. So Laplace transform signal is given as, this is the Laplace transform of a signal. So the value of sigma is nothing but real part of S, for which this integral convergence is called region of convergence. Okay. So ROC consists of all those values of sigma for which CTFT of xt into e to the power minus sigma t converges. Now if we are limiting the values of sigma in certain range, we can ensure that the value of xt into e to the power minus sigma t is absolutely integrable, although xt is not itself absolutely integrable. Okay. So ROC also provides the information about whether xt is Fourier transform or not. इसके लिए so condition for this is that XS must include, or ROC must include j omega axis. Okay. So this is, you can see the ROCs. This is parallel to the imaginary axis. Okay. Now come to the another transform, jet transform, which is basically discrete time counterpart of the Laplace transform and also the extension of DTFT. There are some signals for which we cannot apply DTFT because of convergence issue. So that in those places we can use this jet transform. Again, jet transform plays the same role in discrete domain as your analog, as your Laplace transform in analog domain. Again, it is of two types, bilateral and unilateral. Bilateral is again used for stability, causality and frequency response, and unilateral is a convenient tool for finding out the solution of difference equation. Important thing is their difference equation rather than differential equation. So this is the expression for bilateral jet transform and this is unilateral jet transform. And expression is this by which you can represent the jet transform. And you know, in polar form, jet is equal to r e to the power j omega, where with r as the magnitude of jet and w as the angle of jet. Okay. So from here we can see that the DTFT of xn into r to the power minus n, DTFT of xn into r to the power minus n is equivalent to the jet transform. Okay. So the exponential weighing term r to the power minus n may be decaying or growing with increasing n depending on whether r is greater than less than unity. Okay. So jet transform reduces to Fourier transform on the contour in the complex jet plane corresponding to a circle with a circle radius of unity. So here we can see that if r is 1, then you can say r means this is the unit circle. So if we are calculating the jet transform over this unit circle, so that is nothing but the DTFT. That is nothing but the DTFT, or you can say jet transform evaluated over a unit circle is nothing but the DTFT. Okay. Region of convergence, here the range of values of mod z equals to r, for which the jet transform converges is termed the region of convergence. So ROC consists of those values of r for which the DTFT of x to n into r to the power minus n converges. Also jet transform exists for some signals that do not have a DTFT. By limiting ourselves to a certain range of r, we may ensure that xn into r to the power minus n is absolutely summable, even though xn is not absolutely summable. So what happened if we are multiplying this by this decaying term xn into r to the power minus n, then the now signal can be absolutely summable. So again, ROC can provide the information about whether signal is Fourier transform or not. For this condition is that this unit circle should be overlapped by ROC. So if this unit circle is overlapped by ROC, then you can say the signal is Fourier transform. Okay. And if you want to obtain DTFT from jet transform, then simply put r equals to 1, for which in that case where the ROC is overlapping this unit circle. And this is the summary, you can say. You can see this is the summary, type of signals and spectrum. So for CTFT, DTFT, DFT, Laplace and jet transform, I have shown this. So you can see this and understand that how the comparison is made among all these transforms. So these are for all for in time domain, and these are corresponding frequency domain representation. So you can see this table and understood what I have told earlier. Okay. Now because of lack of time, I am ending it. So these are the references that I have used. for my presentation. Thanks. Thanks a lot.